Welcome to The Explainer. In this series, we dig into complex topics by going straight to the source. And today, we're tackling a real puzzle that's literally right next door, astronomically speaking. We're talking about the moon and its atmosphere, which, believe it or not, is way denser than it has any right to be.
All right, so let's get right into it, because what's going on with the moon's atmosphere is a genuine scientific head-scratcher. You see, for decades now, we've known the moon has something called an ionosphere, basically a charged-up upper atmosphere. The problem? It's way, way stronger than any of our standard theories say it should be. And according to the source material we're looking at today, this isn't just some tiny little anomaly. It might just be a clue that challenges how we think about the physics of the entire cosmos.
So this is the number that really kicked things off. It was discovered about 40 years back. The measurement showed the moon's ionosphere has an electron density of at least 1,000 electrons per cubic centimeter. Now you might be thinking, okay, so what did our theories predict? Well, that's the kicker. Standard theories predicted a density of basically zero, nothing. And as our source author points out, when you expect zero and you find 1,000, that's not just off by a factor of 1,000. It's a miss by infinity. It's a total breakdown of the theory.
Okay, so if the old theories are completely wrong, how does mainstream science try to explain this away? Well, in 2011, a paper came out of NASA's Goddard Space Flight Center that offered up an answer. Let's dig into what they proposed.
The answer? In a nutshell? Moon dust. Yeah, just plain old moon dust. The theory goes something like this. You've got these tiny, fine particles of dust that are somehow just floating way up high above the moon's surface. Then, the sun's UV radiation zaps this dust, which knocks electrons loose. And voila, that's what creates the charged atmosphere we're seeing. It sounds pretty simple, right? Maybe a little too simple.
But wait a minute, where's the proof for all this floating dust? This is where it gets really interesting. Our source points out that the entire theory, the whole thing, is basically built on data from way back in 1971. You see, the Apollo 15 astronauts reported seeing a weird glow on the horizon. They snapped some photos, and then, a full 40 years later, that 2011 NASA paper used those exact same photos to infer, not directly measure, but guess, that there was enough dust up there to make their theory work.
And this, as you can imagine, is exactly where our source material starts to pick things apart. The author begins to poke some pretty big holes in this whole moon dust story by asking some really sharp, critical questions.
So, here's the first big one. If the sky is supposedly so full of dust, why haven't any of our modern orbiters seen it? Think about it. Since 1971, we've had Japan, China, India, and NASA all send these incredibly advanced spacecraft to orbit the moon. If there was really a massive cloud of dust up there, big enough to create this powerful atmosphere, wouldn't we have seen it by now? Why are we still leaning on some fuzzy photos from the 70s? The author's point is pretty clear. If the dust was there, our modern gadgets would have spotted it. Period.
And that leads to an even bigger problem, one that gets into some pretty fundamental physics. The moon has no wind, right? No weather, no thermal currents rising up from the ground to stir things up. It's a vacuum. So what in the world is lifting all this dust off the ground and holding it up against the moon's gravity?
This chart really puts the problem into perspective. I mean, look at this. On the left, you've got the dust, just sitting on the surface where it belongs. But the ionosphere it's supposed to be creating, that's way up there, peaking at 5 kilometers high. 5 kilometers! So the question our source is asking is pretty simple. What kind of invisible elevator is powerful enough to lift tons of heavy dust that high against gravity?
And this, right here, is the author's central point. It's a fantastic critique. In an attempt to explain the mystery of some super lightweight electrons floating around, the moon dust theory ends up creating an even bigger mystery. How did all these heavy dust particles get up there in the first place? You know, the so-called solution is actually a much tougher puzzle than the original problem it was trying to solve.
All right, so if the moon dust theory is, let's say, full of holes, then what's the alternative? Well, our source material doesn't just criticize, it actually proposes a totally different model. And it's one based on an idea that it claims mainstream physics has kind of just overlooked.
This new theory kicks off with a really fascinating premise. Okay, stay with me here. We all know that every single atom has its own little charge field, right? Well, the author argues that when you get a giant body like the moon, which is made of trillions upon trillions of atoms, all those tiny little fields don't just cancel each other out. Nope. They actually add up. They combine to create one single massive charge field for the entire moon, a huge field built from all its tiny parts.
So, a giant charge field around the moon? Cool idea. But how does that explain its atmosphere? Let's see how the author connects these dots and builds a whole new model for what's going on up there.
The author calls this whole process charge recycling, and you can think of it like a four-step cosmic circuit. First, you've got the sun, constantly beaming out a field of charge. Second, the moon kind of acts like a sponge, and it soaks up that charge at its poles. Step 3, that charge actually travels through the moon and then gets re-emitted from the surface, mostly around the equator. And this final step, this rising, recycled charge, that is supposedly the key to the whole thing.
And here it is, the core of the idea. This constant upward flow of charge, it acts like a kind of wind. An extremely fine, totally invisible wind that's just blowing straight up away from the moon's surface. Now, we're not talking about a wind that could lift a feather or anything, but according to this theory, it's more than powerful enough to lift something incredibly light, like an electron.
So when you put these two ideas next to each other, the big difference just jumps out at you. The moon dust theory needs some mysterious, unexplained force to lift the dust first, and then something else, the UV rays, to ionize it. But the charge field theory? It's much cleaner. It proposes that the lifting force and the creation of the ionosphere are part of the same process. It's all done by this charge wind.
And get this alternative theory also has a neat explanation for why the atmosphere seems to stop at that 5-kilometer mark. According to the source, that altitude is basically the boundary line. It's the point where the moon's own local charge field starts to get overpowered by the much, much bigger charge fields of the Earth and the Sun. Once the electrons get that high, they just get swept away.
Okay, so let's wrap our heads around this. What should you take away from all this? Well, the source author lays out a really compelling argument, right? First, they take apart the mainstream moon dust explanation, pointing out some pretty major league flaws in both the data and the basic physics. And then, they don't just leave it there. They offer a brand new model, this charge field idea. And they claim this model doesn't just solve the puzzle of the moon's atmosphere, but it might just point to a huge missing piece in our whole gravity-only view of how the universe works.
And so, in the end, the source material leaves us with a really provocative question to think about. Are weird things like the moon's ionosphere just little local quirks, puzzles that we can solve with a quick fix, like the moon dust theory? Or are they something more? Are they, as the author suggests, little breadcrumbs leading us toward fundamental forces of the cosmos that we are still completely overlooking? A whole new layer of physics we haven't even begun to understand.